Alright, so the ion exchange chromatography is a chromatographic process that allows the separation of ions and polar molecules based on their charge, as well as other forms of chromatography. In ion exchange chromatography, there is a mobile phase which generally consists of buffer solution, and there is a stationary phase which consists of a matrix that contains charged ionizable functional groups. This type of chromatography is subdivided into an ion exchange chromatography and cation exchange chromatography. In anion exchange chromatography, negatively charged molecules are attracted to a positively charged solid support, which is usually beads that provide a positively charged surface, such as a resin quaternary ammonium. In cation exchange chromatography, positively charged molecules are attracted to negatively charged solid support, which is commonly beads that provides negatively charged functional groups such as resin metal sulfate. Ion exchange Ion exchange chromatography is frequently used for the separation and purification of proteins. The basic process of this chromatography can be represented in 4 steps: conditioning or equilibration of the stationary phase, 2. Sample loading, 3. Washing and elution of retained molecules. The first step is the equilibration of the stationary phase to the desired start conditions. The pH and ionic strength of the sample buffer are selected to ensure that when sample is loaded, proteins of interest bind to the medium and as many impurities as possible do not bind. Therefore, the same buffer is used for the equilibration of the stationary phase. When equilibrium is reached, all stationary phase charge groups are bound with exchangeable counterions such as chloride or sodium. When the chloride is equilibrated, the second step is sample application. Depending on the pH of their environment, proteins may carry a net positive charge, a net negative charge, or no charge. This net charge can be determined by comparing the pHi of each protein with the pH of the buffer. Proteins are large biomolecules consisting of one or more long chains of amino acid residues. Amino acids are organic compounds that contain amine and carboxyl functional groups, along with a side chain specific to each amino acid. Depending on the pH of their environment, the amino group can be protonated and become positively charged. The carboxyl group can be deprotonated and become negatively charged. And the side chain of some amino acids can become positively or negatively charged due to the gain or loss of protons. So, the net charge on the molecule can be positive, neutral, or negative. The isoelectric point of or pHi is the pH at which a protein carries neutral charge. At a pH below the isoelectric point, proteins carry a net positive charge, and at a pH above their isoelectric point, they carry a net negative charge. In this example, the pH of the buffer is equal 5. Consequently, protein A has a net negative charge, and both protein B and C carry a net positive charge. In addition, protein C is more positively charged since its pHi is higher than the pHi of protein B. If we apply cation exchange chromatography, protein that has a net positive charge, it will bind to the negative charge beams of the stationary phase. On the other hand, uncharged proteins or those with a net negative charge will not bind. They pass through the column at the same speed as the flow of buffer. When all the sample has been loaded, the next step is column washing. The column is washed with start buffer to ensure that all non-binding proteins have passed through the column. When all the sample has been loaded and the column washed, conditions are altered in order to elute the protein bounce. Most frequently, proteins are eluted by increasing the ionic strength of the buffer, or occasionally by changing the pH. As ionic strength increases, the salt ions compete with the bound component for charges on the surface of the medium, and one or more of the bound species begin to elute and move down the column. The proteins with the lowest net charge at the selected pH will be the first ones eluted from the column as ionic strength increases. Similarly, the proteins with the highest charge will be the most strongly retained and will be eluted last. Protein B has the lowest net positive charge, so it can be eluted first. Then, protein C with the highest net positive charge can be eluted next by increasing the salt concentration. Also, varying the pH of the buffer can be used to affect the separation and to elute the retained proteins. As we've seen, the pHi of protein B is equal to 7 and the pHi of protein C is equal to 9. And so, if you add a buffer with a pH above the isoelectric point of protein B and below the isoelectric point of protein C, the protein will become negatively charged and can be then eluted. The protein C is still charged positively, consequently still retained. Next, protein C can be eluted if we apply a buffer with pH above its isoelectric point, so it becomes negatively charged and it will pass through the column. One of the primary advantages for the use of ion exchange chromatography is the interaction during the separation. Another advantage of ion exchange is the predictability of elution patterns by controlling changes in ionic strength or in the pH of the buffer using different forms of gradients, etc. Thank you.